general relativity, step by step. Last time I made the observation that if a little galaxy here sends out a pulse of light and then another pulse of light, the difference between the two pulses here is delta t, and here it's a bigger difference because of the cosmological expansion term in our metric for the universe. I'm going to quantify that term now. What I'm going to do is I'm just going to make the observation that dr by dt equals 1 over a of t, and so dr equals dt over a of t, and I'm just going to integrate it. And so the distance travelled equals r is this. It's, if we plot 1 over a of t against t, it's this area here. Actually, I'll draw that area in a different colour because I'm going to have to improve this diagram. And I'm going to shade it in orange. That's pulse 1. Now pulse number 2, green. Pulse number 2 was sent out a little bit later, and it goes along there, down there, down there, down there, and arrives here. I'm going to shade that green area there. And now I'm going to make the observation that the orange area equals distance for pulse number 1 equals the green area, which equals the distance travelled for pulse number 2. Okay, and you see that it's set off a bit later, and in that time there we've got this extra sort of area here. We can see that we're losing this amount of r here, but we're gaining this one here. So what that tells me, if I can just express it in algebraic notation, that means that delta t emit upon a of t emit equals that area there, well, to first order at least, equals delta t obs upon a of t observed. So that tells me that delta t obs over delta t emitted equals, which way round, a of t obs divided by a of t emit, delta t. And then of course what I'm going to do is to consider delta t to be the distance between two successive peaks of light. That's going to be delta t, emit. And so what that tells me is that the frequency of the light, which is proportional to 1 over the delta t, obeys this law. Omega obs divided by omega emit equals a of t emit over a of t obs. And that is a redshift. So this is the origin of the redshift. This is quite a subtle argument. The orange area, the fact that the orange area equals the green area is the same thing as saying that r is unchanged between the pulses. So r is unchanged, and you say, well, it can't be unchanged because the universe is expanding. Yes, but we are using co-moving coordinates, so we have nailed the coordinate system to the galaxy. That is the strength and the difficulty and the conceptual hardness of this particular approach. Nevertheless, we've got this beautiful expression here for cosmic redshift, and we normally express that using a z term. So normally this is a definition of cosmic z, the redshift z. 1 plus z equals, by definition, omega emitted divided by omega observed. okay, which equals A of T obs divided by A of T emitted. Okay, and that's our definition of Z. That defines Z. Yeah, that's a definition of Z for my cosmic redshift. And what I'm going to do in the next screencast is I'm going to discuss small z, or actually small, oh dear, I'm not sure what's happening there, small changes. Okay, stop there, stop.